Imagine standing inside the Serapeum of Saqqara, a vast subterranean tunnel carved deep beneath the desert sands. In front of you rests a black granite box weighing 100 tons. You run your hand along its surface. It is not simply smooth. It is chemically flat, a level of refinement that challenges everything we think we know about ancient craftsmanship. Yet the true impossibility hides in the corners. Shine your light into the inner angle where the wall meets the floor. What you see is a razor-sharp 90-degree intersection. Ask any modern machinist. Polishing a perfect inner corner inside a granite chamber is a nightmare. A rotating tool leaves a curve. A hand tool leaves a radius. These corners defy that expectation. They are so precise that even a beam of light cannot slip into a gap. The question hangs heavy in the stagnant air. How did the ancient Egyptians fit a tool inside this confined space and finish the stone with such flawless geometry without modern machinery? To understand what truth lies hidden in this stone, we must slow down our perception. Let the noise of modern industry fall away until only the quiet breath of this tunnel remains. Feel the cool touch of the granite. Focus on the mystery etched into its surface. The journey into the microscopic world of ancient engineering begins now. To understand the magnitude of this mystery, we need to face a scientific reality that stands like a granite wall in front of us. Every material has a measurable hardness. This is not a vague impression of toughness. It is a quantifiable resistance defined by the Mohs scale, a simple yet powerful ranking that orders minerals from the softest to the hardest. At the bottom is talc with a value of 1. At the top is diamond with a perfect 10. Between them lies the entire world of stone. Copper, the primary metal used by the ancient Egyptians, according to mainstream scholarship, sits at a hardness of 3. Limestone, a soft and workable stone, sits at 3 or 4. But granite, the stone used for the most enigmatic ancient structures, is a 7. Granite is an interlocking blend of quartz, feldspar, and mica. Quartz crystals alone are capable of scratching steel. Yet we are told that ancient workers shaped and polished this unforgiving material with tools made of copper, sand, and time. Here is the physical paradox. A softer tool cannot cut a harder material without a more powerful intermediate abrasive. Copper cannot cut granite. A chisel of 3 cannot meaningfully shape a stone of 7. This is not an opinion. It is the physics of material science. It is the same reason a fingernail cannot carve glass. The hardness gap creates a barrier that no amount of skill or human endurance can simply wish away. Mainstream Egyptology proposes a solution: abrasive sand. Sand contains quartz, which matches the hardness of granite. The theory holds that if you push a copper saw loaded with sand back and forth for long enough, the grains will slowly erode the stone. And to be fair, this works for limestone. Modern experiments have proven that soft stones can be shaped with primitive methods. But applied to granite, this explanation begins to crumble. Sand abrasion is chaotic. It explains a rough cut or a broad surface, but it cannot explain the mirror-like finishes or the impossible geometry we see in the Serapeum. Abrasion distributes energy randomly. It does not produce chemically flat surfaces, perfect straight lines, or interior corners sharp enough to cut your finger. To accept the orthodoxy, we must imagine armies of workers using tools that dull in minutes, yet somehow achieving tolerances that modern factories struggle to reproduce. This is where the obstacle grows into something vast. We are not looking at a single lucky artifact. We are staring at millions of tons of granite. The Nile Valley is lined with obelisks, statues, and boxes weighing up to 100 tons, all shaped with a consistency that suggests a systematic technology, not sporadic brilliance. The sheer volume of high-precision granite work defies the sand and time model. The counter-argument is simple. Sand creates a radius. Machines create corners. Hand tools create variations. Machines create symmetry. When you look at the deep, decisive saw cuts in the basalt of Abusir, or the spiral grooves on a granite drill core, you are not seeing the marks of patient rubbing. You are seeing the signature of power. The boundary of the unknown begins here. We stand between two worlds. One is the world of established scholarship, where tools are simple and time is the great equalizer. The other is the world suggested by the physical evidence, where precision is routine and capability is undeniable. The granite refuses to lie. It challenges us to look again, to question our assumptions, and to admit that something in the ancient toolbox is missing. We now step out of the realm of legend and into the realm of evidence. Imagine approaching ancient Egypt not as a tourist, not as a believer in myth, but as a forensic investigator entering a silent crime scene. The desert has swallowed the workshops, the tools, and the blueprints, yet the stones remain. They hold the fingerprints of a forgotten craft. Every cut, every corner, every polished surface is a clue. The granite blocks are not relics of simple artisanship. They are data. They are testimony. They form a silent archive of techniques that should not exist in the age to which they are assigned. Picture the Nile Valley thousands of years ago. Temples rising, obelisks gleaming, statues towering over plazas. Somewhere behind these colossal achievements, there must have been a place where all of this was made. A workshop, a laboratory, a center of engineering whose methods allowed workers to shape crystalline rock with the precision of a modern machine shop. We do not see the facility directly. Instead, we see its byproducts scattered across the landscape like fragments of a vanished civilization. This is where our investigation begins. Not with written records, not with myths, with the stone itself. The surface of an unfinished block becomes a witness. A drill core becomes a confession. A saw mark becomes a trace of the blade that carved it. The more closely we examine these clues, the more they resist the explanations offered by conventional archaeology. The ancient Egyptians left behind monuments of staggering beauty, but beneath that beauty lies an industrial mystery. Something happened here that does not fit neatly into our understanding of early civilization. Something powerful enough to reshape granite, basalt, and quartz with ease. Something precise enough to leave surfaces flat within fractions of a millimeter, and corners so sharp they challenge even modern machining standards. As we walk through quarries, temples, and tunnels, we are not merely observing ruins. We are tracing the ghost of an entire technological system. The evidence is not arranged neatly. It is scattered across centuries and sites, yet it forms a pattern. Every drill hole, every unexplained groove, every flawless contour. Together, they whisper a single message. The workshop existed. Its tools existed. Its methods left marks that cannot be erased. Our task now is to read those marks with the eyes of an engineer, to reconstruct the capabilities of a culture whose mechanical knowledge may have far exceeded what is currently believed. We stand at the threshold of this deeper investigation. To cross it, we must examine the first unmistakable signature of advanced stoneworking. It lies not in a temple, but in a small cylindrical object pulled from the heart of granite itself. A drill core that should not exist. Our investigation leads us to one of the most unsettling pieces of physical evidence ever recovered from ancient Egypt. It is not a statue. It is not a block. It is not a grand architectural feature. It is a small cylindrical fragment of granite discovered in the 19th century by the meticulous archaeologist Flinders Petrie. He catalogued it as core number 7, but the name does not capture its significance. This object behaves like a message carved directly into stone. A message that says the ancient Egyptians possessed a level of mechanical power far beyond the tools we attribute to them. To understand why this core matters, imagine drilling into granite. Granite is a crystalline rock composed largely of quartz, which is harder than steel. Modern drill bits use diamond abrasive and heavy machinery to penetrate it. Even with that advantage, the process is slow. The feed rate, the distance the drill advances per revolution, is typically measured in thousandths of an inch. A high feed rate is dangerous because it risks overheating, bit failure, and catastrophic fracture. Now examine core number 7. Running around its circumference is a spiral groove, a helical indentation that records the exact motion of the tool that cut it. This groove is not random. It has spacing, it has rhythm, it has depth. These markings allow us to calculate the feed rate of the drill that produced it. Petrie measured the groove and made a startling discovery. The drill advanced into the granite at roughly 1/10 of an inch per revolution. That feed rate is extraordinary. It surpasses what modern diamond drills can safely achieve unless massive downward pressure is applied. To create a groove like this, a tool must have been rotated with high speed while simultaneously being forced downward with tremendous weight. Engineers have attempted to reproduce this pattern with hand tools and copper drills. The results do not match. Copper bends, sand disperses. The drill chatters and skips. The grooves are uneven and shallow. The feed rate is too slow. The spiral of core number 7, by contrast, is consistent, sharp, and unmistakably produced by a stable, powerful mechanism. The implications become even more troubling when we consider the hardness of the materials involved. Granite is a 7 on the Mohs scale. Copper is a 3. For a drill to leave such a mark, the cutting edge must have contained something far harder than copper. Yet no such tool has been found. If the ancients relied solely on sand as the abrasive, the spiral groove should appear chaotic. Sand does not behave like a rigid cutting edge. It strikes the surface at random angles. It leaves scattered abrasion, not a clean mechanical helix. Core number 7 is not the trace of erosion. It is the trace of engineering. We must also consider the implied force. Experiments conducted by modern machinists suggest that to achieve a feed rate comparable to the one recorded on the core, the drill would need to be pressed downward with thousands of pounds of pressure. Human strength cannot generate that. A team of workers rotating a drill by hand cannot generate that. The weight and speed required point to a machine. Whether powered by hydraulics, counterweights, or an unknown mechanism, the tool behind this core operated with industrial authority. The core itself is only half the story. The hole from which it was extracted displays matching grooves. Both pieces behave like two halves of a mechanical signature left in stone. Together, they challenge every assumption about the technological limits of the ancient world. If we ignore this evidence, we reduce the investigation to myth. If we confront it, we are forced to rethink everything we believe about ancient engineering. Core number 7 is a whisper from the past, but it is a whisper delivered with the clarity of a drill bite. It tells us that ancient Egypt possessed the ability to penetrate one of the hardest stones on earth with a force and precision that should not have existed at the time. It tells us that the workshop we imagine was not powered by copper chisels and hand-operated drills. It was powered by something more advanced, something capable of reshaping granite with ease. Our next step in this forensic journey takes us away from the drill and toward another signature of lost technology. This time, the evidence appears not inside a hole, but across the surface of stone. It is a mistake carved into basalt, a slip so violent and so sudden that it reveals the speed and power of the tool that made it. It waits for us in the ruins of Abusir. Our investigation now takes us to a site that appears outwardly unremarkable. Abusir is quiet, windswept, and often overlooked by visitors who seek the grandeur of Giza or the mystique of Saqqara. Yet here, among scattered basalt paving stones, lies one of the most telling signatures of ancient technology. Not a finished artifact, not a polished masterpiece. Instead, a mistake, a slip. A moment when a tool cut deeper than intended and left behind the unmistakable evidence of its own power. Imagine kneeling beside one of these basalt blocks. Basalt is tougher than granite. It is dense, brittle, and unforgiving. Working it by hand is slow and exhausting. A craftsman using copper saws and sand abrasives would not leave decisive deep cuts. He would leave scratches and broad scars created by hours of grinding. His errors would be gradual. The blade would wander off course slowly, gently drifting as fatigue set in. But what we see at a Busser is not gentle. It is instantaneous. Running across several of these stones is a line so straight and so uniform that it appears machine-guided. Parallel striations follow the path of a saw blade that moved with consistent pressure and high velocity. The surface shows a regular spacing of grooves that suggests a repeating mechanical action. These marks resemble the results of a circular saw or a reciprocating industrial cutter. They are not the chaotic scratches produced by abrasive slurry. They show direction. They show rhythm. They show purpose. Now examine the point where the saw slipped. This is the moment that turns curiosity into certainty. If ancient workers were using simple copper saws with sand, a mistake would appear as an uncontrolled wobble. It would be shallow. It would be slow. It would take time for the operator to realize the drift and correct it. Instead, the gouge at a Busser plunges dramatically into the stone. The blade bites deep in a single instant, creating a vertical scar that reveals tremendous downward force combined with significant forward momentum. This is the behavior of a powered tool. A blade moving with speed. A blade carrying inertia. A blade that cannot stop on a dime because it is being driven by something stronger than human muscle. The depth of the gouge is too great for hand sawing. The crispness of the lower edge shows that the stone fractured under sudden mechanical impact, not slow abrasion. Engineers who have studied these marks compare them to accidental cuts made by high-torque saws in modern workshops. The signature is the same. To create such a mark, the saw must have been under heavy load. The kerf, the width of the cut, remains consistent along the length of the stone. This consistency indicates a rigid blade with minimal flex. Copper does not behave this way. Under pressure, copper bends and distorts. A copper saw under heavy load would buckle long before it produced a straight, uniform channel in basalt. The tool that made this cut behaved more like hardened steel or an alloy far beyond what the archaeological timeline allows. Some scholars have suggested that the saw was weighted with stones and pulled back and forth by teams of workers. This explanation fails when confronted with the violent nature of the slip. Human-powered saws do not accelerate fast enough to cause such sudden deviation. The blade would slow as it entered the stone, not surge downward into it. The cut at a Busser records a moment of lost control, the kind of loss that only happens when a mechanical system overwhelms the operator. It is the scar of a machine, not a manual tool. The parallel lines adjacent to the gouge deepen the mystery. They are evenly spaced, as if created by teeth or a repeating surface passing over the stone. No copper saws with teeth have been found in Egypt, and traditional sand sawing does not produce this effect. The spacing suggests a regular oscillation, a mechanical vibration, or possibly the imprint of a large rotating blade. Whatever the mechanism, it operated with consistency beyond the ability of human hands. Now step back and consider the broader context. These paving stones were not hidden deep within a ceremonial chamber. They were part of the working surface of an ancient complex. They were functional, not symbolic. No religious purpose required this level of precision. No ritual demanded the straightness or depth of these cuts. The marks are the byproduct of an industrial process. A process carried out not in secrecy, but in routine. A process that relied on tools more advanced than anything we have recovered. What we see in a Busser is not artistry. It is manufacturing. It is the residue of a machine shop without the machines. It is the echo of a technology that left no tools behind. It carved its presence into stone with undeniable force. The mistake on the basalt is not a flaw. It is a confession. It tells us that the ancient Egyptians used a powered cutting device capable of high torque, high speed, and deep penetration. It tells us that the orthodox toolbox is incomplete. Abuser forces us to confront a simple truth. When a tool slips, it reveals its nature. The saw marks on these stones reveal power, stability, and mechanical force. They reveal a level of engineering that does not belong to a world of copper chisels and sand abrasives. They reveal a workshop that has vanished, leaving only the scars of its machines behind. Our investigation now moved from cuts and grooves to a different kind of precision. Instead of looking at errors, we will examine perfection. The next signature of lost technology is written not in stone floors, but on the faces of colossal statues. It appears in curves so symmetrical that they rival digital modeling. It challenges the notion that ancient hands alone shaped these monuments. It is time to confront the symmetry of the pharaohs. Our forensic trail now leads us from the quarry floor to the silent gaze of a pharaoh. The statues of ancient Egypt are known for their grandeur, but hidden beneath their beauty lies a mathematical precision that defies the tools attributed to their time. To understand the scale of this mystery, stand before the colossal head of Ramses at Luxor or Memphis. Look closely at the contours of the face, not as a historian, but as an engineer. Begin with the jawline. On the right side, it sweeps upward in a smooth arc. On the left, it mirrors the same curve with astonishing accuracy. Measure the cheeks. Their bulges match within fractions of an inch. Observe the lips. The curvature is balanced, continuous, and subtly complex. Then examine the eyes. Their spacing, their angles, and the depth of their sockets align with geometric harmony. You are not looking at approximate symmetry. You are looking at engineered symmetry. Modern sculptors, even those with decades of experience, struggle to achieve this level of bilateral perfection by hand. The human eye introduces inconsistencies. A chisel hesitates. A hammer slips. The natural movements of the wrist create micro-deviations that accumulate across the surface. To produce a statue of this size with such flawless symmetry would require constant measurement, repeated adjustments, and extraordinary patience. Yet the statues of Egypt display this precision across dozens of colossal works, many carved from granite, one of the hardest stones on earth. Christopher Dunn, a master machinist and engineer, approached these statues with precision instruments rather than assumptions. Using calipers, straight edges, and optical tools, he documented the geometry of Ramses and other monumental heads. His measurements revealed consistent radii across the cheeks and forehead, as if the sculptor used a fixed mechanical guide. The curves behave like sections of defined arcs, not freehand work. Certain surfaces appear planar when viewed from the right angle, suggesting they were flattened with a level of control impossible to achieve with pounding stones. One of the most striking observations concerns the geometry of the ears. In hand carving, ears often differ slightly. The angle shifts. The curvature changes. Yet on these statues, the ears are symmetrical not only in overall size, but in the subtle undulations of their internal structure. This would require either an extraordinary sculptor with superhuman consistency or a process that allowed the artist to reference a fixed template. Now, consider the scale. These statues often stand over 20 feet tall. The face alone may be several feet in height. Maintaining symmetry on such a massive surface is exponentially more difficult than on a small sculpture. Any slight variation becomes magnified. The larger the carving, the harder it is to keep proportions balanced. Yet here, the symmetry holds. From jaw to brow, from ear to ear, the proportions remain stable and consistent. Imagine the process required to achieve this using the orthodox toolkit. The sculptor would need to mark reference points with string and ink, constantly stepping back to compare left and right sides. The granite would resist each strike, fracturing unpredictably. A misplaced blow could ruin days of work. Achieving uniform curvature across three-dimensional surfaces would demand continuous recalibration, but granite does not allow fine, delicate removal with copper chisels. It breaks with force, not subtlety. Consider also the polished surfaces. Many faces show mirror-like finishes that reflect light with clarity. This level of polish requires abrasives much finer than sand. It requires compounds capable of refining the crystalline structure of granite. Stone tools cannot achieve this effect reliably across an entire monumental sculpture. When viewed as a whole, the statue behaves not like a hand-carved object, but like the result of a guided shaping process. Some engineers have proposed the possibility of a large mechanical lathe, not one that spins the statue entirely, but one that allows controlled rotation or indexing. Such a device could standardize curves and maintain symmetry. There is no physical evidence of such machines, yet the geometry of the statues suggests a method that involved rotational reference or guided cuts. The symmetry challenge becomes even more compelling when examining multiple statues of the same pharaoh. Their features match so closely that they appear to have been produced from a template. Modern manufacturers produce identical sculptures using molds or CNC machines. Hand carving rarely achieves such uniformity, especially at monumental scales. Yet ancient Egypt presents statue after statue with nearly identical facial geometry, differing only in minor stylistic choices. Critics argue that skilled artisans could achieve this with enough time. But skilled artisans working with copper chisels cannot overcome the hardness of granite. They cannot maintain consistent curvature across massive surfaces using tools that dull after minutes of use. They cannot polish a face to mirror quality with sand alone. And they cannot replicate the same face across multiple statues with such precision unless a standardized method existed. The faces of Ramses and other pharaohs are not simply artistic representations. They are engineering puzzles. The curves and planes align with such accuracy that they invite comparison to modern coordinate measuring machines. When these statues are digitally scanned, the data reveals symmetry patterns that match industrial tolerances. Stand before one of these colossal heads. Let your eye trace the transition from cheek to jaw, from brow to temple. There is no hesitation in the stone. The lines flow with controlled geometry. Every contour shows intention. Every angle shows mastery. The face is not just carved. It is engineered. What does this imply about the workshop of the ancient Egyptians? It suggests a level of planning, measurement, and mechanical assistance far beyond copper tools. It points to a forgotten system of metrology, a method of defining curves and planes with repeatable accuracy. It implies the presence of guiding structures, templates, and perhaps even machinery that allowed sculptors to shape granite with consistency and speed. The statues challenge us to reconsider the boundaries of ancient craftsmanship. If they were produced by hand alone, then the artisans possessed skills that defy physical limitations. If they were produced with assistance from advanced tools, then our timeline of technological development is incomplete. Either conclusion demands a revision of the story we tell about the ancient world. As we leave the gaze of the pharaoh behind, we carry forward a growing realization. The evidence is cumulative. The drill cores point to mechanical drilling. The saw marks point to powered cutting. The symmetrical faces point to guided shaping. Each artifact alone is intriguing. Together, they form a pattern, a technological fingerprint scattered across temples and tombs. Our journey now shifts from individual clues to the broader implications of precision itself. We will examine measurements so exact that they rival modern engineering standards. We will confront surfaces flattened to absurd tolerances and angles so perfect they behave like machine references. To understand the full magnitude of the mystery, we turn to the work of a modern expert in precision, a machinist who brought the language of industry to the monuments of Egypt. To move deeper into the mystery, we must shift from observing stone with the naked eye to measuring it with the precision of modern industry. Many archaeologists describe the monuments of Egypt in terms of symbolism, mythology, and artistry. Christopher Dunn approached them with a different language, the language of tolerances, surface flatness, angular deviation, and geometric error. He walked among the ruins, not as a historian, but as a machinist trained to see the world through thousandths of an inch. Dunn spent decades working in advanced manufacturing. In that world, nothing is assumed. Everything is measured. A surface is not smooth unless an instrument proves it. A line is not straight unless the deviation is recorded. A corner is not square unless the inspection equipment confirms the angle. This mindset prepared him to look at Egypt with a level of scrutiny that had rarely been applied to ancient stonework. The first object he examined in detail was one of the massive granite boxes inside the Serapeum. These boxes weigh upward of 70 tons and are carved from some of the hardest stone available in Egypt. Archaeologists often describe them as sarcophagi. Dunn approached them as if they were machine parts. He placed precision straight edges against their surfaces and used feeler gauges to test flatness. The results were shocking. What appeared to be simple stone walls were flat to within 2/10,000ths of an inch. In modern manufacturing, this level of precision belongs to engineered components, not ceremonial objects carved with primitive tools. A surface this flat does not happen by accident. It is the product of a controlled process. It requires stable tooling, intermittent measurement, and abrasives capable of removing material with consistent accuracy. Copper chisels cannot achieve this. Sand abrasion cannot achieve this. Even modern stoneworking shops struggle to maintain such tolerances across a surface several feet long, yet the Serapeum boxes achieve it on multiple faces with uncanny uniformity. Dunn then examined the internal corners. He found them almost perfectly square. Measuring the deviation from a true 90-degree angle, he recorded tolerances comparable to those found in industrial enclosures. These were not rough corners chipped out by hand. They were sharp, geometric, and consistent. The tool that created them must have been guided by a reference system that maintained stability and precision. His next observation concerned the symmetry of certain statues and architectural elements. Using straight edges, laser alignment tools, and mechanical gauges, Dunn measured curves, angles, and parallel surfaces. Many features displayed exacting geometry. Cylindrical shapes maintained constant radius. Flat planes showed almost no warp. Linear edges ran true over long distances. These findings suggested not only advanced tools, but advanced measuring practices. Someone in ancient Egypt understood metrology, not as an abstract concept, but as a practical necessity in their craft. Dunn also noted machining marks, circular patterns resembling tool paths, linear striations matching the feed direction of cutting implements, surface textures that mirrored those created by modern rotary tools. While archaeology often attributes these to erosion or accidental wear, Dunn recognized the signatures of mechanical processes. To those accustomed to machining, the marks are familiar. They speak the same technical language found on parts fresh off a mill or lathe. What disturbed him most was not a single measurement, but the accumulation of them. Precision appears not in one object, but across a vast range of monuments and artifacts. The builders of Egypt worked with consistency. They repeated geometric relationships. They reproduced angles accurately. They mirrored surfaces with intentional control. These patterns imply standardized methods. They imply reference tools that enforced accuracy. They imply a technological approach, not a purely artistic one. The orthodox explanation insists that these achievements were the result of extraordinary patience and countless hours of labor. Dunn countered that patience cannot overcome material hardness. Time cannot substitute for mechanical stability. A craftsman armed with a copper chisel cannot produce a surface flat to a few 10,000ths of an inch, no matter how long he works. At some point, the tool itself becomes the limiting factor. A soft tool cannot refine a hard stone beyond its own properties. The stone will dictate the finish, not the skill of the hand. Dunn proposed a different interpretation. He believed the ancient Egyptians possessed tools and technologies capable of guiding, measuring, and shaping stone with high precision. These technologies may not resemble our modern machinery, They may have operated on principles unfamiliar to us, but the evidence suggests that the builders were not guessing. They were not improvising. They were executing processes with accuracy that required planning, control, and technical understanding. Consider the implication. To achieve this level of precision, there must have been a system, a tradition of engineering knowledge, a workshop environment where tolerances mattered, a culture in which stone was not merely carved, but machined. Such a system would require the ability to measure straightness, squareness, and flatness. It would require a framework of standards, much like modern industries rely on reference blocks, jigs, fixtures, and calibrated instruments. Yet none of these tools have been found. What remains is the stone itself, the final product. The granite boxes, the statues, the architectural features. Their precision becomes the instrument through which we reverse engineer the lost methods of their creation. Dunn argued that the absence of tools is not evidence of primitive craftsmanship, but evidence of technological fragility. Metal corrodes. Wood decays. Tools are recycled. Stone endures. Standing before a serapeum box with instruments in hand, Dunn saw not a burial container, but an engineering artifact. He saw a surface too perfect for copper, a corner too sharp for abrasive slurry, a finish too refined for hand labor. The box behaved like something produced in a controlled workshop, not a ceremonial tomb. This shift in perspective changes everything. If ancient Egypt possessed the ability to measure and execute stonework with such precision, then the monuments must be reinterpreted. They are not merely artistic expressions or symbolic structures. They are technical achievements that point to a deeper layer of knowledge, one that challenges the conventional narrative of human development. As Dunn continued his measurements, the pattern became unavoidable. Too many surfaces were flat. Too many angles were perfect. Too many features displayed repeatable geometry. These were not anomalies. They were the fingerprints of a forgotten science. The metrology of ancient Egypt forces a question that echoes through the desert. Who were the builders in terms of their technical understanding? What tools did they use? What principles guided their craft? And how much of that knowledge has been lost? To explore these questions further, we must now turn to an object that defies traditional explanation entirely. An artifact so delicate, so precise, and so mechanically suggestive that it has puzzled scholars for more than a century. It sits quietly in a museum case, yet it behaves like a component removed from a machine. It is the schist disk of Sabu. Our investigation now shifts from monolithic granite to something far more delicate, something so thin and fragile that it should not exist if carved with the tools assigned to its time. In a quiet gallery of the Cairo Museum rests an object unlike anything else from the early dynastic period, the schist disk of Sabu. It dates to the First Dynasty, more than 5,000 years ago. Its age alone is astonishing. Yet the true mystery lies in its shape. The disk measures roughly 24 inches in diameter. It is carved from schist, a brittle metamorphic rock composed of flaky minerals. Schist does not behave like granite. It does not withstand heavy hammering. It fractures. It delaminates. A single misaligned strike sends thin layers peeling away. No sculptor chooses schist for complex forms because the stone simply refuses to cooperate. Yet the disk of Sabu is not just complex. It is intricate. Imagine standing in front of it. For a moment, it resembles a wheel, then an impeller, then a mechanical component whose purpose is unclear only because we lack the machine it once belonged to. 3 curved blades extend from the central hub, sweeping outward with aerodynamic grace. The blades taper elegantly, forming thin veins that would be difficult to produce even with modern rotary tools. The central aperture is perfectly circular. The transitions between surfaces show continuous curvature, as if guided by a template or jig. To understand the impossibility of this artifact, consider the properties of schist. Even today, stoneworkers approach it with caution. The material flakes unpredictably. It cannot be shaped with force. It must be cut with controlled abrasion or stabilized with resin. But ancient Egypt possessed neither diamond-edged tools nor chemical stabilizers. According to orthodoxy, the disc must have been carved using stone hammers and copper chisels. This explanation becomes untenable when examined closely. A hammer blow would shatter the veins. A chisel would pry the layers apart. The slightest vibration could destroy hours of work. Now look at the uniformity of the blades. Each one curves with identical sweep. Each one maintains a consistent thickness. There is no evidence of correction, no sign of accidental chipping, no unevenness between the arms. The geometry suggests intentional design. It suggests the use of a rotational reference or guided cutting path. The disc behaves as if it were shaped on a spindle or through a controlled machining process that maintains symmetry and balance. Engineers who study the disc often remark that its form resembles impellers used in pumps or turbines. These modern components channel fluid through rotational motion. Their efficiency depends on the precise curvature of the blades. While it would be speculative to claim that the disc served a similar purpose, the resemblance raises questions about the design principles at work. Why would a culture with only copper tools create a shape that mirrors modern mechanical engineering? Archaeologists classify the disc as a ceremonial object. This explanation avoids the technical challenge by placing the disc in the realm of symbolism. Yet ceremony does not require such delicate geometry. Ceremony does not require uniform blades or a central aperture machined with apparent rotational symmetry. A ritual artifact could be simple. It could be carved from soft limestone or clay. But the disc is neither simple nor soft. Its design is functional, not ornamental. The context of its discovery deepens the mystery. The disc was found in the tomb of Prince Sabu, a noble of the First Dynasty. His tomb contained pottery, stone bowls, and other objects typical of early Egyptian burial practices. Nothing else in the tomb displays comparable complexity. Nothing else suggests advanced craftsmanship. The disc stands alone, as if it belonged to a different tradition entirely. To understand the magnitude of this anomaly, recall that the First Dynasty predates the pyramids by centuries. According to Orthodox chronology, Egyptian technology was still primitive at this time. Copper smelting was in its infancy. Stone shaping techniques were limited. Yet the disc of Sabu behaves like the product of a mature understanding of geometry and controlled tooling. Look again at the thinness of the blades. Some portions measure only a few millimeters thick. Achieving this requires fine removal of material with minimal vibration. A handheld chisel cannot maintain such delicacy. The tool pressure alone would crack the stone. The consistency of thickness across the entire disc indicates a stable process, one that allowed the sculptor to remove material gradually and evenly. There is also the matter of internal transitions. Between the central hub and the outer rim, the surfaces curve smoothly, without abrupt changes. This continuity is characteristic of machine surfaces. It suggests that the shaping tool maintained a constant relationship to the axis of the disc. Whether the object rotated or the tool followed a predetermined path, the outcome is the same. The process appears guided. Some researchers have attempted to replicate the disc using primitive tools. Their models shatter. Their surfaces crumble. Their blades chip inconsistently. None have produced a replica that matches the original. The material simply does not tolerate the methodology. When modern sculptors attempt to recreate the disc with power tools, the process becomes manageable. Using diamond blades, sanding drums, and rotary instruments, they can shape schist with precision. Yet even then, the work requires caution. The stone remains fragile. Vibrations must be minimized. Tool paths must be controlled. The similarity between the required modern methods and the apparent ancient results raises an uncomfortable question. How did the Egyptians accomplish this without vibration-free tools? The disc is not only technically challenging, it is conceptually advanced. Its geometry implies understanding of rotational symmetry and dynamic flow. Cultures typically develop such forms only when function demands them. Impellers, flywheels, and turbine blades arise from engineering needs, not ceremonial imagination. The disk of Sabu hints at a function we do not fully grasp. Its design feels purposeful. Some researchers speculate that the disk could have been mounted on a shaft. The central hole suggests attachment. The angled blades suggest directional flow. While the function cannot be proven, the shape invites mechanical interpretation. At the very least, it demands technical curiosity. When placed within the broader context of our investigation, the disk becomes part of a larger pattern. The drill cores reveal controlled rotational cutting. The saw marks reveal high-speed blades. The statues reveal guided shaping of granite. Now the disk reveals delicate machining of brittle stone with rotational symmetry. These are not isolated anomalies. They form a chain of evidence pointing toward an ancient capability that operated with precision across multiple materials and forms. As we stand before the schist disk in its glass case, we confront an object that should not exist in the archaeological record as we understand it. Its craftsmanship violates the limitations of its era. Its geometry challenges our assumptions about ancient design principles. Its fragility exposes the inadequacy of the copper and stone toolkit. The disk asks a question as sharp as the granite corners of the Serapeum. What kind of workshop could produce such an object? What kind of tools could shape schist into aerodynamic forms? What kind of knowledge guided the hands that crafted it? To answer these questions, we must step back and consider the implications of everything we have uncovered so far. The evidence is no longer confined to a single site or a single artifact. It spans dynasties. It crosses disciplines. It forces us to examine the ancient world not only through the lens of archaeology, but through the eyes of engineering, physics, and material science. Before moving to the next phase of our investigation, it is time to address the viewer directly. We stand on the threshold between known history and potential revision. The next breath of the narrative invites participation in that journey. We now stand before a growing constellation of evidence. The drill cores that record impossible feed rates. The saw marks that reveal the strength of powered cutting. The colossal statues that display engineered symmetry. And the schist disk that behaves like a component removed from a forgotten machine. Piece by piece, the story of ancient Egypt begins to shift. The line between art and industry becomes blurred. The past grows deeper. The questions grow louder. If this journey has awakened your curiosity, if you feel the mystery tightening its hold as each clue comes into focus, this is the moment to stay with it. The investigation is only beginning. There are still fragments of truth scattered across the desert. Still measurements waiting to be taken. Still connections that will reshape how we see the ancient world. So if this exploration of lost technology speaks to you, if you want to continue unraveling the puzzle carved into stone across millennia, consider subscribing to the channel. Your presence supports the search. Your attention keeps the investigation alive. Together, we can follow the trail of evidence wherever it leads. The next chapters will take us beyond the forge and into the world of imagination, grounded in engineering. We will step into what might have been. We will explore the implications of a civilization whose capabilities have been hidden in plain sight. The mystery does not fade. It grows stronger with every discovery. To understand the implications of everything we have uncovered, we must allow ourselves to cross the boundary between evidence and imagination. Not imagination as fantasy, but imagination as a tool for reconstruction. Imagine standing on the Giza Plateau, not as it appears today, silent and wind-worn, but as it may have been its prime. The sun rises over the Nile. The river glows like polished copper. Across its banks, the air hums with activity. Granite blocks arrive on barges from Aswan, their surfaces raw and unshaped. Workers guide them onto ramps, not with primitive struggle, but with a practiced efficiency that suggests familiarity with heavy loads. The sound that fills the plateau is not the chaotic clang of copper striking stone. It is something steadier, something rhythmic, a pulsing mechanical cadence. Picture a long row of cutting stations near the river. Large frames hold saws embedded with abrasives harder than quartz. The blades move with a smooth, sustained motion, powered not by teams of exhausted laborers, but by a system that channels energy from the river itself. The Nile, with its eternal current, becomes the beating heart of an industrial landscape. Water wheels turn. Counterweights lift. Ropes tighten and release in cycles that convert flowing water into mechanical force. Granite blocks are cut with stable motion. The blades bite without hesitation. Fine powder gathers beneath each table, the dust of a stone reshaped by controlled power. Move deeper into the plateau. Enter a workshop where shaping takes place. Imagine massive pillars of granite mounted on rotational stands. A steady tool glides across their surfaces, guided by reference arms and fixed pivots. The resulting curves are exact. The angles are consistent. The statues carved here are not guessed into existence. They are engineered into being. The sculptor becomes a technician, not in the modern sense, but in the sense of someone trained to understand the behavior of stone under controlled forces. Now, walk into a quieter chamber, a place where finishing takes place. Granite boxes lie on their sides, their interiors exposed. Artisans inspect the surfaces with straight edges made of a lost alloy. They check flatness. They test the sharpness of corners. They refine angles with tools that vibrate at precise frequencies, vibrating with a power that moves through stone, like a tuning fork extended into another domain. The sound is soft but penetrating. The stone responds. Microscopic particles fall away, leaving behind a surface that gleams like polished metal. Turn to the schist workshop. Here, the fragile stone is supported on dampened mounts that reduce vibration. The craftsman touches the surface with a tool that glides rather than strikes. Movement is minimal. Pressure is controlled. The veins of the disc form slowly and deliberately, shaped with a method that treats schist not as an enemy, but as a material that can be coaxed into complexity if handled with precision. All across the imaginary landscape, the Nile serves as the energy source. The river is not worshipped merely as a symbol of life. It is harnessed as a force of industry. Through canals and diverted channels, water is guided into systems that lift, turn, rotate, and press. The Egyptians did not need combustion or electricity to achieve mechanical power. They had gravity. They had flowing water. They had time to refine these principles into something stable and repeatable. From the quarries to the workshops, from the river to the plateau, everything forms a coherent system. Not one of modern steel and engines, but one of levers, counterweights, water power, abrasive science, and mechanical guidance. A system capable of producing large-scale precision without violating the laws of physics. A system that leaves behind the very marks we see in granite today. Imagine walking through this ancient industrial district as night falls. Torches flicker. Workers move deliberately. The sound of tools quiets, replaced by the deep murmur of the Nile. The machines slow. The blades rest. Yet the stones retain the memory of their transformation. They keep the evidence etched into their surfaces. They preserve a record of controlled force, guided motion, and intentional design. This reconstruction is not a claim. It is a bridge, a way to conceptualize a technological tradition that has been erased except for the marks it left in stone. When we look at the monuments today, stripped of all machinery, all workshops, all infrastructure, we see only the final stage of a vast process. The finished product remains. The tools have vanished. The industrial landscape has dissolved, yet the granite remembers. The industrial Nile presents a tantalizing possibility. It suggests that ancient Egypt may have pursued a technological path different from our own. Not electricity and metal engines, but hydraulics, vibration, geometry, and mechanical advantage. a system rooted in nature, scaled by human ingenuity, and refined through centuries. If this vision holds any truth, then the monuments of Egypt are not only temples and tombs. They are the surviving artifacts of an engineering tradition that used the natural world as its power source and the precision of stone as its language. Our investigation now turns to a crucial question. If such machines existed, why have none survived? Why do we not find their remnants buried in the sand? Why do we see only the products, never the tools? The answer may lie not in what the Egyptians built, but in what later generations chose to preserve. With each clue we uncover, the silence of the archaeological record grows louder. The drill cores reveal rotational power. The saw marks reveal high-torque machinery. The statues reveal guided symmetry. The precision reveals metrology. The schist disk reveals delicate, controlled shaping of brittle stone. Yet for all of this evidence, one question now rises with overwhelming force. If the ancient Egyptians possessed the tools capable of producing such work, then where are those tools? The paradox is stark. The products of advanced technique survive in abundance. Blocks weighing tens of tons, statues towering over plazas, granite boxes shaped with industrial tolerances. Yet the tools that shaped them have vanished entirely. This absence has often been used as proof that such tools never existed. But the logic of archaeology demands a deeper examination. The first explanation is simple and practical. Metal was precious in the ancient world. Bronze and copper were valuable commodities. Iron was rare and often imported. When a civilization collapses or transitions through periods of turmoil, metal is not buried for posterity. It is melted down. It is reforged into weapons, household tools, or agricultural equipment. A saw blade weighing hundreds of pounds, if made of bronze, would be worth too much to leave behind. It would be recycled again and again until no trace remained. History offers countless examples. Entire armies have vanished from the record because their armor was melted for coinage. Bronze statues from antiquity survive only as bases because their bodies were melted for weaponry. The lack of surviving metal does not prove its absence in antiquity. It proves its value. Now consider the possibility of non-metallic tools. We assume that machines must be made of metal because modern machines are. But ancient engineering may have followed a different path. Wooden frames, stone bearings, rope-driven pulleys, and ceramic guides could accomplish more than we typically imagine. Wood decays, rope rots, ceramics shatter. None of these materials would survive thousands of years in the Nile environment without preservation. If the tools were not made of bronze or iron, their absence becomes even more understandable. But the most provocative explanation is conceptual rather than material. What if the tools we are looking for do not resemble our expectations at all? What if the method used by the ancients did not require blades in the conventional sense? What if the cutting force was not applied through a sharp edge, but through controlled vibration or resonant energy? Imagine a tool that causes stone to fracture along microscopic planes by matching its internal frequency. Quartz crystals vibrate at stable, predictable rates. Granite blocks contain billions of them. If a device could induce vibration at the right frequency, the stone could weaken and shear with minimal force. This is not speculative mysticism. It is material physics. Ultrasonic cutters today use similar principles to slice through hard substances with surprising ease. If the Egyptians developed a mechanical or acoustic method of inducing resonance, the resulting cuts would appear clean, fast, and mechanically stable. And such a tool could leave no metal remains. Consider also the schist disk. Shaping schist with vibration, rather than impact, would solve the problem of its brittleness. The veins could be carved with a vibrating tip that removed thin layers without striking the surface directly. The uniformity of the curves would follow naturally from a guided oscillation. If this seems far-fetched, remember that ancient cultures often approached problems from entirely different angles than we do today. We assume that the path to advanced tooling must follow the same trajectory as ours. But civilizations can take alternate technological routes. They may emphasize different principles. They may discover effects that we overlook or rediscover much later. Even if we assume purely mechanical tools, their disappearance remains plausible. A large copper saw blade used in quarrying could be reforged countless times. The handles made of wood would rot. The abrasives used in cutting would disperse. The workshop frames would collapse. A civilization can leave behind mountains of stone, but no trace of the machines that shaped it if those machines were made of perishable materials. Another factor complicates the archaeological record. The workshops of Egypt were temporary facilities. They existed near construction sites, not as permanent stone buildings. When a project was completed, the site was dismantled. Tools were taken to the next location. Structures made of timber or mud brick decayed long before modern archaeologists arrived. The machines we seek may have been mobile, modular, and tied to the rhythms of construction. When the workforce moved on, nothing durable remained. There is also the possibility of intentional erasure. Civilizations sometimes undergo ideological shifts. Temples are repurposed. Symbols are defaced. Knowledge falls out of favor. In periods of instability, tools associated with a previous era might have been destroyed or melted. The new rulers may have had no interest in preserving the methods of the old. Yet for all these explanations, the paradox retains its tension. The absence of tools is puzzling precisely because the presence of their work is undeniable. The stone does not care whether its creator left behind a workshop. It records the force applied to it with perfect honesty. It preserves the signatures of lost capability, even when the tools themselves have vanished. The paradox invites a shift in perspective. Instead of asking why the tools are missing, we must ask why the evidence in the stone is so abundant. The granite boxes, drill cores, saw marks, and statues tell a story that cannot be erased. They are the footprints of a technology that once existed. The tools may be lost, but the results remain, waiting to be interpreted. Our investigation now moves toward the realm of possibility. If ancient Egypt followed a different technological path, then their methods may not align with our assumptions. The next step is to explore that divergence, to consider what kind of knowledge could produce such work, to imagine the technological identity of a civilization whose mastery of stone hints at an understanding we have barely begun to grasp. This brings us to a profound idea. Perhaps ancient technology was not oriented toward metal or machines the way ours is. Perhaps it was oriented toward vibration, resonance, geometry, and the natural forces of the world. Perhaps the tools were not missing because they never existed in physical form as we imagine them. Perhaps they existed as principles absorbed into the craft, intangible yet powerful. To understand this possibility, we must step back even further. We must explore not only the physical implications of lost technology, but the conceptual implications. We must consider that physics itself may have been interpreted differently by those who built in stone with such mastery. The deeper we travel into the mystery, the more we are forced to confront an uncomfortable truth. Our understanding of ancient technology is shaped entirely by the path our own civilization has taken. We assume that progress follows a single line. We assume that the climb from stone tools to electricity must occur in a specific order. We assume that the logic of our technological evolution is universal. Yet the evidence carved into the monuments of Egypt suggests a different story. It hints at a path that did not mirror our own. In the modern world, technology is defined by electronics, metal alloys, combustion engines, and digital systems. Precision comes from computer numerical control, laser measurement, and industrial automation. Our tools are built on the manipulation of electricity and the refinement of metals. But what if the ancient Egyptians chose a different foundation? What if their technology did not rely on metals in the same way? What if they mastered natural forces that we have relegated to niche applications? Consider vibrations. In our era, vibration is a side effect, something to be dampened, something to be controlled. Yet vibration can cut through stone. It can soften material. It can guide fracture. It can act as a tool. We use ultrasonic scalpels in surgery. We use vibrational cutters in manufacturing. We use resonant frequencies to measure the internal structure of objects. But these applications are small and specialized. We do not build our civilization on resonance. The ancient Egyptians may have. Consider geometry. Today, geometry is a tool for design, but rarely the engine of a technological system. In Egypt, geometry guided architecture, spiritual belief, astronomical alignment, and measurement. It was not merely a mathematical discipline. It was a worldview. If their technology was rooted in geometry, then precision would emerge naturally from their understanding of shape, proportion, and spatial harmony. Their tools may have been guided by geometric constraints rather than mechanical templates. Consider the Nile. To us, it is a geographic feature. To them, it may have been a power source. Flowing water can drive saws, drills, hammers, and lifting systems. We use water in hydropower plants, but the principle is modern. The Egyptians may have used it centuries earlier in ways we do not yet understand. Our assumptions blind us. We search for iron saws because we use iron saws. We search for bronze lathes because we use bronze when metalworking is limited. We search for engines because our machines depend on combustion. But the Egyptians may have used tools that left no easily identifiable remains. Tools made of organic materials. Tools based on controlled motion and natural physics. Tools that fit into a technological paradigm that diverged sharply from our own. We often claim that the Egyptians were primitive because they lacked electricity, but they may have possessed a mastery of mechanical energy that we have forgotten. We claim that their tools were simple because no advanced tools have survived. But the absence of tools does not negate the presence of sophisticated results. We claim that their achievements were slow because we assume that complexity requires time. But complexity can also arise from efficiency. In the present, we evaluate ancient knowledge through a narrow lens. We ask whether they had metal. We ask whether they had engines. We ask whether they had wheels. But these questions betray our assumptions. They ignore the possibility that ancient civilizations explored principles we have discarded or never fully developed. What if the Egyptians understood resonance in a way that surpasses our own? What if they harnessed water power with elegance and scale? What if they built their tools not as mechanical replicas of modern equipment, but as extensions of natural forces? If this is true, then their technology becomes invisible to us because we are searching for the wrong artifacts. Think of how future archaeologists might interpret our world if only the stone survived. They would find skyscraper foundations, but no steel beams. They would find roads, but no cars. They would find tunnels, but no trains. They might conclude that humans dug large holes and lived in them, unaware of the machines that made them possible. The absence of tools would distort the interpretation of the work. This is the position we find ourselves in with ancient Egypt. We see the work, we see the precision, we see the geometry, we see the scale, but we do not see the tools. Our modern instincts urge us to dismiss the evidence, to assume coincidence or extraordinary manual skill. But the stone insists otherwise. The stone insists that technology existed. Not our technology, but a technology equal in sophistication. This realization forces a connection to the present. It challenges our arrogance. It challenges our belief that progress is linear. It challenges our assumption that we stand at the apex of human knowledge. The Egyptians remind us that a civilization can discover truths, exploit natural principles, and build wonders without leaving behind the machines that made them possible. As we consider this possibility, the mystery deepens. The past is no longer a dim corridor behind us. It becomes a mirror reflecting our own limitations. It becomes a teacher showing us that human ingenuity takes many forms. It becomes an invitation to rethink our understanding of what is possible. Our journey now moves from speculation to reflection. Having traced the evidence and imagined the system that could have produced it, we must confront the philosophical implications. What does this mean for our view of history? What does it mean for our understanding of human capability? And what does it mean for the legacy of a civilization that built its identity not on metal or electricity, but on mastery of stone? With these questions in mind, we enter the next phase of our investigation, a contemplation of what it means for knowledge to be discovered, lost, and rediscovered, a meditation on the fragility of understanding, a recognition that the desert may be hiding more than ancient monuments. It may be hiding entire chapters of human achievement. We have now walked through a labyrinth of evidence carved into the very bones of the ancient world. We have traced the impossible inner corners of the Serapeum. We have examined the spiral groove of a drill core that should not exist. We have studied the deep scars left by a blade moving with overwhelming force. We have stood before the engineered symmetry of a pharaoh's face. We have measured surfaces that rival the tolerances of modern industry. And we have witnessed the delicate impossibility of a schist disk carved 5,000 years ago with a precision worthy of a modern workshop. As we gather these threads together, a pattern begins to emerge. Not a pattern of myth or romantic speculation, but a pattern born from stone, measurement, and physical evidence. Each artifact becomes a piece of a larger mosaic that challenges our understanding of ancient capability. Each measurement, each mark, each impossible surface whispers the same quiet message. There was more happening here than the simple tools of orthodoxy can explain. Now, at the threshold of the final act of our journey, the focus shifts. This is the moment when investigation gives way to reflection. This is where the facts we have collected begin to illuminate something deeper about the nature of knowledge, the fragility of memory, and the story of human civilization. We often imagine the past as a straight line stretching backward from the present. We imagine that ancient people stood at the beginning of a long upward climb toward progress. But when we look closer at these artifacts, when we examine the builders through the lens of engineering rather than assumption, that straight line begins to bend. It becomes a curve. It becomes a spiral. It becomes a reminder that history is not a ladder, but a landscape with peaks and valleys, with lost paths and forgotten summits. Standing before the precision of ancient Egypt, we confront a profound idea. Knowledge is not guaranteed to survive. Mastery can rise, flourish, and disappear. Entire traditions can vanish while their works remain, leaving future generations to puzzle over the methods behind them. The stones of Egypt reveal not only the skill of their creators, but the impermanence of human understanding. They show us that civilizations are not just built of monuments. They are built of ideas, and ideas can be lost. As the desert wind moves across the plateau, as the last shadows of the day stretch across the ancient walls, a quiet realization settles in. The people who shaped these stones were not our intellectual ancestors in a primitive age. They were human beings standing on their own peak of discovery. They were craftsmen, engineers, and thinkers who mastered principles we no longer possess. They explored a technological path that diverged from our own, and somewhere along the arc of time, that path faded from sight. This reflection brings us to the heart of the mystery. The ancient Egyptians were not defined by their limitations. They were defined by their achievements. They were not bound by the simplicity we impose upon them. They were capable of mastery that forces us to rethink what we believe about human potential. Their work challenges us to remain humble in the face of history. It challenges us to acknowledge that progress is not inevitable. It is fragile. It requires preservation. Without that preservation, even the brightest flame can dim. Now, as we move into the next stage of reflection, we will explore what this means not just for our understanding of the past, but for our understanding of ourselves. We stand now at the summit of our investigation, looking back across the scattered trail of evidence left by a civilization that mastered stone in ways we struggle to comprehend. The deeper we travel into the past, the clearer one truth becomes. The word primitive is not a measure of what people were. It is a mirror reflecting what we assume about ourselves. When we call the ancients primitive, we shield our pride from the possibility that they achieved something we cannot. We comfort ourselves with the idea that progress moved forward in a straight, predictable line. We place ourselves at the peak of that line, convinced that all humanity before us was climbing toward the knowledge that we now possess. But the stones of Egypt disrupt that narrative. They stand as silent counter-arguments to our arrogance. These monuments show that civilizations can rise to extraordinary heights without following the same technological path we have taken. They show that mastery does not require electricity or metallurgy as we define it. It requires insight. It requires observation. It requires a willingness to explore the natural forces of the world with depth and patience. The builders of Egypt may have known things we have lost. They may have walked a road of discovery that diverged from ours long before our own sciences took shape. And what they left behind reveals something profound about the nature of human knowledge. Discovery is not permanent. Mastery is not guaranteed. A civilization can hold the keys to a powerful understanding of the world and still lose it. The knowledge that shapes an age can fade when its custodians disappear. Ideas can vanish while the works they created endure. Stone remembers long after memory fails. Their achievements challenge the myth of linear progress. They remind us that the human story is not a single rising slope. It is a tapestry woven from countless forgotten peaks. Many civilizations may have reached summits whose traces now lie buried beneath sand, sea, and time. The Egyptians were not climbing toward us. They were standing on their own mountain. And from that height, they carved their knowledge into granite so deeply that even 5,000 years could not erase it. This realization changes the way we see the ancient world. It also changes the way we see ourselves. It reveals the vulnerability of our own age. If entire systems of advanced stoneworking could disappear, then what does that say about the technologies we depend on today? Our world is built on fragile foundations. Digital, metallic, electrical. Remove one thread and the entire structure trembles. Without power grids, microchips, or fuel, our achievements would collapse in days. But the Egyptians built in stone. Their work survives because they chose the material least likely to fail. Perhaps that is why their monuments feel immortal. Not because they were meant to impress the gods, but because they were built with the quiet confidence of a people who understood that the desert is a patient guardian. Stone endures. Stone speaks across ages. Stone carries the last whisper of knowledge, long after the voices that shaped it have been silenced. Their story humbles us. It invites us to loosen our grip on certainty and embrace mystery as a teacher rather than an obstacle. It reminds us that wisdom can disappear. It warns us that brilliance can be forgotten. And it offers a simple, powerful truth about the human condition. We are not the pinnacle of history. We are participants in a cycle of discovery and loss. The builders of Egypt reach out to us across millennia, not with words, but with the precision of their stone. They remind us that genius is not bound to time, that mastery can bloom in any era, that the human mind is capable of wonders we have not yet rediscovered. And as we reflect on everything we have seen, the monuments reveal their final lesson. Knowledge is not owned. It is borrowed. It is fragile. It must be nurtured, protected, and passed forward. Otherwise, it slips away like water through open hands, leaving only the echo of what once was. As we step back from the towering monuments and the precision carved into their stone, a deeper understanding begins to unfold. The mystery of ancient Egypt is not only a question of tools, engineering, or forgotten methods. It is a reflection of something profoundly human. Beneath the weight of granite and the polish of impossible surfaces lies a truth about our own nature. We hunger for meaning. We strive to leave something behind. We reach for permanence even as time moves steadily past us. When we look at the work of the ancient Egyptians, we are seeing more than technical mastery. We are seeing an expression of purpose. We are seeing the desire to shape the world so precisely that it resists the chaos of time. We are seeing the echo of a civilization that understood its own impermanence and tried to forge monuments that could outlast every storm, every war, and every forgetting. Their work speaks to us because we share the same longing. We want to understand the world. We want to build something that survives. We want to believe that our achievements carry meaning beyond the span of our lives. The Egyptians pursued that desire with stone, geometry, and mastery of materials. We pursue it with data, machines, and digital memory. Yet the impulse is the same. We are all trying to carve our existence into the fabric of time. At the heart of this investigation lies a reminder of our vulnerability. Civilizations rise not because they possess limitless strength, but because they discover a single insight that unlocks new possibility. The Egyptians found their insight in stone. They learned how to work with it, how to control it, how to shape it with forces that remain mysterious to us. Their knowledge elevated them. It allowed them to build monuments that still command awe thousands of years later. But insight is fragile. It depends on continuity. It depends on teaching, practice, and the passing of knowledge from one generation to the next. When that chain breaks, the insight is lost. What remains is only the stone. The living knowledge that once animated the tools fades like breath on cold air. This is not only the fate of ancient civilizations. It is the fate of every human endeavor. The knowledge we hold today is no more secure than the knowledge held by the Egyptians. If our systems falter, our own mastery can vanish just as theirs did. This recognition invites compassion for the builders of the past. They were not primitive. They were not fumbling in the dark. They were reaching toward the same light that we reach toward now. They succeeded in ways we struggle to understand. And they remind us that human potential is not confined to any particular age. It is a universal force that appears whenever curiosity, skill, and imagination converge. In the silent faces of the statues, in the polished corners of the granite boxes, in the spiraling grooves of a drill core, we see the imprint of that force. We see the hands of people who dared to shape the world with precision and intention. We see the reflection of our own hopes and doubts. We see the truth that human beings have always been capable of greatness and always vulnerable to forgetting. The mystery of ancient Egypt touches something inside us because it speaks to a shared journey. A journey defined not only by discovery, but by loss. A journey that reminds us to remain humble, to cherish knowledge, and to honor the achievements of those who came before us. Their stone whispers a lesson that reaches across time. Greatness is possible. Knowledge is precious. And the story of humanity is deeper than the fragments we have preserved. This connection to the human spirit prepares us for the final descent of our narrative. A gentle release from inquiry into reflection. A moment to let the weight of the mystery settle into silence. A transition from thought into rest. Let the noise of questions begin to settle. Let the weight of the mystery grow quiet. Allow the mind to loosen its grip on the edges of certainty. For a moment, imagine the desert at night. The heat of the day has faded. The wind carries a cool breath across the sand. The stars gather above the plateau, bright and steady, watching the monuments the way they have watched them for thousands of years. Picture yourself standing beside a block of ancient granite. Its surface is cool beneath your hand. The stone is smooth, unwavering, and still. It carries no urgency. It holds no expectation. It asks nothing of you. It simply exists, solid and calm, anchored in a silence that stretches across millennia. Feel that steadiness. Let it flow into your body the way the desert wind flows across the landscape. The questions that pressed against your mind begin to drift away. You no longer need to solve the puzzle. You no longer need to search for answers. The stone beneath your hand reminds you that not every mystery demands resolution. Some mysteries offer peace. Some invite you to rest in the space between knowing and wondering. Imagine the soft rhythm of your breathing, filling the quiet tunnel of the Serapeum. Each inhale feels like stepping deeper into the cool shadows. Each exhale releases the remnants of the day. Above you, the ceiling arches gently into darkness. Around you, the granite walls hold the memory of hands long gone. Their silence comforts you. Their permanence steadies you. Let the stillness grow. Let it rise slowly from the stone, through your fingertips, into your arms, and into your chest. Feel your heartbeat slow. Feel your thoughts soften. Feel the weight in your shoulders settle into a calm, grounded ease. The ancient world surrounds you, not as a puzzle, but as a shelter. You are safe here. You are held by the quiet. You are supported by the timeless calm of a civilization that shaped stone with mastery and intention. Let that calm become your own. Let it guide you gently toward rest. The desert night deepens. The air cools further. The world narrows to the steady rhythm of your breath and the solid presence of the granite beside you. There is nothing else to hold, nothing else to chase. Only this moment, only this stillness. When you are ready, allow your eyes to grow heavy. Let your thoughts settle into the quiet spaces between words. Let your mind drift like sand carried by a gentle wind. The stone remains. The night remains. And you drift inward, toward the quiet center of yourself, carried by the calm of an ancient world. This has been another story carried along the endless river of time. A journey through mysteries etched in granite and guarded by the silence of the desert. As the night settles around you, and your breath grows slow and steady, let the ancient world drift gently into the distance. Its questions can rest for now. Its wonders will wait for you. If this exploration of forgotten knowledge has brought you calm, curiosity, or a sense of connection to something larger than yourself, consider following the channel. There are many more journeys waiting beyond the horizon. More stone to examine. More clues to uncover. More forgotten paths to walk together. For now, allow the quiet to guide you. Feel the weight of the day dissolve. Let your thoughts soften until they settle like dust across the desert floor. You are safe. You are warm. You are drifting into a deep and peaceful sleep. Good night, dreamer of ages. May the echoes of ancient worlds carry you gently into rest.